Today we're looking at some more Calculus 2 practice problems, focusing on finding the volume of surfaces of revolution using the disk method. So what is the disk method? Imagine we take this triangle and we revolve it around the y-axis. Notice this little slice right here. When we revolve it, it becomes a cone, right? And that little slice turns into a disk, hence the disk method, right? So what is the volume of this disk? The volume of this disk, delta V, is a little cylinder, right? So it's base pi r squared, and the height of this little cylinder is some delta y, right? Some little change in y. And we're going to use that to find the volume of the entire thing using integration. So, like I said, we're going to add all these disks together here. We're going to sum up all of these disks while having an infinite amount of disks. This limit takes care of that. And what does a limit turn into? A limit of a sum just turns into an integral. So now you can see the slices are very thin, and we're going to be adding up all those infinitely thin slices from 0 to the height of this cone, right? So this is the equation we're working with, pi r squared delta y. So let's look at this. They ask us to revolve the shapes around the y-axis and find the volume of the solid. So let's start with this shape right here. This shape, when we revolve it around the y-axis, the way that you draw them is by going down the axis that you're revolving and copying it and then mirroring it to the other side and then connecting the identical points. So this point came from there and this point came from there. And as you can see, this makes a pretty good little like bowl shape. And then when we revolve that little slice around, it's going to create a little disc where the radius of that disc is the radius that we're worried about. So this slice right here is kind of like the radius of this disc. So we care a lot about this slice, right? This slice. Let's see. The volume is going to be pi integral. Where are these slices right here? This is why we care about this slice a lot, because we're going to be coming back to it. Where does this arbitrary slice move from and to? Well, it starts down here at 0, and we're adding it to all these slices all the way up to y equals 4. So 0, 4. And we know that this slice is a delta y width, right? Which becomes a dy in the integral. So if we have y bounds here and a dy here, we better have a function of y on the inside. So how can we represent the displacement between this function and this function in terms of y? So in the other video, area between curves, we looked at vertical displacement. Now we're looking at horizontal displacement, which is right to left. So where do all of these slices start? Here at this function. And where do they end? Here. If for some reason, like, we were to chop this off and go straight up, this slice right here would be different than this slice, like we looked at in the last video, because this one is starting here and ending here, whereas this slice is starting here and ending here. So we would have to do two separate integrals. We did a little bit of that in the last video, and we're going to do some more in this video, right? So now let's look at the volume, right? We want a function of y here. How can we represent the radius as a function of y, right? Because our formula is pi integral r squared dy. So we need to find what is r. Well, r is just the displacement, because we know that this displacement, this slice becomes the radius down here. So we can see it's starting at this function x squared and ending at this function 0. So it's x squared, right? No, because we need it as a function of y. So let's just change it. If y equals x squared, then x equals the square root of y. And technically plus or minus, right? Plus or minus the square root of y. But we are already in the positive x direction. So we're just going to keep it as the positive square root of y. So the radius is represented as the square root of y minus 0. You can see we're starting here at the square root of y, and we're ending here at, or like we're starting here at x equals the square root of y, we're ending here at x equals 0, right? So r can just be represented as the square root of y minus 0, or the square root of y. So that's going to come in here for our radius function, which means the volume becomes pi 0 to 4 of y dy. Right, so volume is pi. When you integrate y with respect to y, you get 1/2 y squared. We're valuing that between 4 and 0. So it's going to be pi 1/2. 4 squared is 16. So it's going to be 16 halves pi, or 8 pi. We don't really care about the units, and we're okay to leave it in pi because this is calculus, not physics. Okay, so let's look at another problem. Let's revolve this triangle around the x-axis. What's it going to give us? Well, go down the axis that you're revolving around, mirror it to the other side, connect the identical points. So as you can see, we get a cone. And when we revolve that little slice around, it's going to give us a little disc. And you can see the radius of the slice is just this displacement again. And it typically happens that way. So what is this function, right? We need volume equals pi r squared. No, pi integral r squared. Volume and the dy. So it's pi. What are we integrating from and to? Well, you can see those slices are going to start here and end here at 1, 2, 3, 4, or yeah, 1, 2, 3, 4, right? So we're integrating from 0 to 4. What is r though? R is given by the displacement between this function and this function. We know that this is x equals 0. What is this? X equals what? So what I want to do is find the equation of this line. It was not given. We know that y equals mx plus b. We know b, it's the y-intercept 4. Can we find m? Well, it goes down -4, and it runs 2. Rise is -4, run is 2. That means m is rise over run, -2. So this line can be written as y equals -2x plus 4. But like I said, we need x, not y. So let's solve it for x. Y minus 4 equals -2x, and x equals y minus 4 over -2. This is a good radius function, but let's make sure that it's correct. Right here, y equals 0, right? What is the radius? The radius goes from here all the way to here and is 2. So let's plug that into our radius function. Plug in y equals 0, and we get -4 over -2, which is positive 2. So that gives us the correct radius at the bottom. Let's also check it at the top. What happens when you plug in 4 for y? You get 4 minus 4 over -2, which is 0. And at the top, this top slice has a radius of 0 because it's at the very top, right? So this looks like a good radius function to me. Let's square -1/2 y minus 4 dy. Now at this point, your professor may allow you to just use the calculator to solve these integrals. This one I'll do by hand, but they pretty much will stop caring about whether or not you can do this integral, right? Because you should definitely be able to do this integral if you got this far in calculus, right? So, but let's just do it. Pi, when we square that -1/2, it's going to come out as a 1/4. We're going from 0 to 4 of, let's see, y minus 4 squared. I'm looking at this right here. Let's FOIL it out. We're going to get y squared minus 8y plus 16 dy. Now this is a bit easier integral. Pi over 4. When you integrate y squared with respect to y, you get 1/3 y cubed. When you integrate -8y, you get -8 over 2, or -4y squared. And when you integrate 16 with respect to y, you get plus 16y. Finally, we're going to evaluate all of that at 4. So let's see, we have that pi over 4. We have a 1/3. What is 4 cubed? 4 cubed is 64. minus 64 plus 64, right? Looks good to me. So this minus 64 and 64 cancel. We are left with pi times 64 over 12. And finally, 64 over 12 is the same thing as 32 over 6, which is the same thing as 16 over 3 pi. Is this right? Well, let's just check it. We already know what the volume of a cone is. Isn't it just pi times h over 3 times r squared? And we're actually going to prove this equation in the next video. We're going to prove the volume of a cylinder, cone, and sphere using this disk method. So let's just make sure that our answer is right. Pi, what is the height of this cone? 4, right? Because of this right here. And what is the radius? 2. We're going to square 2. And we're going to get 16/3 pi. See? Same answer. Which way are you going to do it on the test? Well, do it this way and then check it that way, right? Okay, so finally, let's look at this one. You can see that there's two different kind of displacements. This slice right here goes from this function to this function, whereas this one is a constant. It just goes from this one to this one. So let's find the equation of this line right here. Let's see, y equals mx plus b. We know that b is 5. Let's find m. M is the rise over the run. We can see that it rises -1 while it runs +2. So m is rise over run, so it's just -1/2, right? So y equals -1/2 x plus 5. But like I said, we have a dy slice, which means we need the radius as a function of y, right? Like x as a function of y. So let's solve it for x. We get y minus 5 equals -1/2 x, which means x equals -2 times y minus 5. Okay, so let's see. This top volume is represented by pi. Where is it going from and to? It's just going from 4 to 5, right? From 4 to here to 5. The radius we just said was -2 y minus 5. We're squaring that radius, and then we have a dy. So dy, function of y, y bounds. Check, check, and check, right? So now let's do volume. It's going to be pi. We're also going to get a 4 when we square this -2 here, right? And then we just have y minus 5 squared. And I don't know why I did the lengthy integration on the other one, because we discovered this tool called u substitution, which would make it probably a bit easier. Du equals just dy. So this becomes the integral of u squared du. And let's just change the y bounds. If we plug in 5 into u, we get 5 minus 5 and we get 0. When we plug in 4 into u, we get 4 minus 5, which is -1. So these are, instead of going from 4 to 5, we're going from -1 to 0 now. So volume equals 4 pi 1/3 u cubed, evaluated at 0 and -1. So it equals 4 pi 0 minus -1/3, which is just 4/3 pi. Okay. And let's do this one now. Volume is going from pi, it's going to 0 all the way to 4. The radius is constant though. The radius is constant. So we can just pull it right out of the integral. The radius is a constant 2 squared dy, right? So now we have 4 pi. When you integrate y, you just get, or when you integrate dy, you just get y. And we're evaluating y at 4 and 0. So that's going to give us 16 pi. Right? So instead of boxing it up. Volume, the total volume is equal to the volume of the cone on top, which was 4/3 pi. And we're going to add that to the volume of the cylinder that we made or 16 pi. Finally, that's going to give us, let's see, 16 pi is really 48 pi over 3. 48 plus 4 gives you 52 pi over 3. Could we have done this one using geometry? Let's see, and we'll check our answer. If you were to revolve it, this part would move to here, and that would create a wide cylinder, right? And when you revolve that cone on top, the one that's here, it almost makes like a silo thing that they use on the farms, right? So let's find the volume of this one. We know that this thing has a radius of 2 and a height of 1. And do we know the formula for volume of a cylinder? Yes. And that's why we were able to pull out this r squared here, because of that constant radius. So it's pi r squared height. Let's see, let's see, it has a height of 4 and a radius of 2. So let's see, this one on top becomes h over 3 pi r squared. So 1/3 pi 2 squared, so 4/3 pi. Check. This one right here becomes pi r squared times height, 16 pi. So check. So the total volume would be this value added to this one, which we found to be 52 pi over 3. So that is how you find the volume of surfaces of revolution using the disk method, right? And in the next video, we're going to prove the volume of a cone and sphere and cylinder using the disk method. Then we'll move on to other volume methods like the washer and shell methods.